I wanted to do a walkthrough for system components and functionality for energy storage systems. I'm going to be covering a lot of the details here, discussing the Enphase energy storage system, how it all works, etc. But and for the most part, the same applies for any storage system out there. And so, and I have kind of one slide to show an example of that in a minute, where the functionality is still the same, just but it depends a little bit based upon the type of system that's there. So this Enphase energy storage system includes several components. Okay, first is the microinverter, which is attached to the solar modules, which are fed into or installed to connect to the IQ combiner and Envoy. The Envoy is the computer that basically manages and communicates to all the devices in the system. And there's a smart switch or controller, a gateway, etc. Different terminology is used across the board for different systems. And then there's the battery unit. In this particular case, we're talking about an InCharge 10T or 5P, which is the common batteries that are used for the Enphase system. The next slide here, we talk a little bit about what the smart controller is and what it can and what it does and its purpose. So the smart controller switch or gateway is basically look where we have the main transfer switch or interrupting relay circuit that isolates the system from the grid in the case of a power outage. This enables us to have power still on the residence for the backup loads and to prevent power from coming from the backup system or micro system or microgrid, as some people like to call it, and keeping it safe for people working on the other side, or whether they're working on the grid or the electric main service panel, etc. It's also a central location for where all the components are terminated and landed. When I say terminated, I'm talking about where the circuits go with circuit breakers or landing on terminal buses, etc., for the wiring for the system. So the backup power is comes from here. The battery circuits come into here. The solar comes into here. The computer that manages everything comes into here to make sure all the power is provided to what's supposed to be off-grid or backed up and controlled by the system, and as well as allowing for power from the utility come in as well whenever it's needed. So kind of everything kind of comes together in the central location. The combiner system. Now, some systems would have this built as part of the battery system, but in the Enphase system, everything's modular and individual components to be serviced on. It does tend to take a little bit more space on the wall with all these multiple components everywhere. And there's other systems that are just all-in-one, but maybe not such a large capacity and capable as the Enphase system. So the IQ combiner computer, right, it monitors and controls everything, right? It talks to all of the smart devices, which is the controller, the microinverters, and everything. The batteries, right, to be more specific. And it reports the system or the information to the data cloud for your monitoring application on your phone or the web, etc. And it allows us to do service on systems remotely to verify how things are performing, what they're doing, etc. And it's also a central location for the circuits for the solar. So all the circuits that go into a solar array for the different solar modules that are tied to the microinverters, for the Enphase microinverters, they all come into this box, right? And they can be turned off and on there, as well as the computer is inside of this in the back side of the panel there. This is the battery component. There's 10 Ts. Those are now kind of being phased out, and the 5Ps are taking their place. So inside the 10 Ts or 5Ps are individual battery packs, and each of the individual battery packs are tied to multiple inverters. Inside the 10T, there should be 12 microinverters and 3 different batteries, and so that's 4 microinverters per battery. The 5P has 1 battery and 6 microinverters attached to the 1 battery. These microinverters are hybrid inverters, which means they go both ways. They bring power in from a supply source to charge up the batteries, as well as discharge power from the batteries to the grid or to the backup loads. The 10T is a 10 kilowatt battery, and the 5P is a 5 kilowatt battery. And the 10T and 5P vary a little bit in how much power they can peak output, and that's like an instantaneous load that comes on, like say an air conditioner or something like that, or a toaster oven, or even an oven, or anything like that, microwave, all of a sudden ramps up really high to a high demand load when it first kicks on, and then it levels off and stables off after a couple seconds, or maybe even 1 second or a few seconds, whatever it is, for depending on the device. So the peak is higher on the 5P with the newer type system than it is on the 10T, but both of them have the max continuous output, which is what it can maintain as an output for a long period of time. So both are basically rated for the same. So the 10T would have more battery capacity, twice the capacity of the 5T, but the 5P has twice the capacity of output for the instantaneous power for the surge, right? A surge of power is needed to start up a device, which makes it good for higher demand appliances and components, while the 10T would be better for long-term stability because it's a bigger battery capacity. So that's basically how those are built, right? You have the battery, you have the inverters, and those are all in the enclosure of whatever the system is. Okay, so here is a general layout of a system, and I put the battery in the center for the Neovolta as an example. As I mentioned, I had a slide for this. So the Neovolta is an example of a system that's all in one, where the smart switch, the battery, and the controller, and the computer, and all the stuff, and all the even the combiner for where the loads and circuits come together are all inside the cabinet. So it makes it for a smaller footprint, and everything inside the cabinet is modular, but it brings everything together in one kind of compact location, and it makes it nice to have less of a footprint inside your available space, whether it's on the wall outside or inside of a garage. On the top left corner is a solar and a microinverter there. What's nice about this particular system for Neovolta is you don't need microinverters. It can be tied directly into the battery system, or you can use microinverters. It doesn't matter whichever way your solar is functions or installed, then either works. And then you have some non-backup loads, which is whenever it's advisable to have, if you're some loads that aren't backed up by the battery system, and those are typically going to be appliances that have a huge amount of power draw to them and would really just deplete your battery very fast if always in constant use. I put an oven on there as an example because an oven, you typically would bake something for an hour or so, and it could pull anywhere between 3 to 9,000 watts at a time, maybe even 10,000 watts, depending on what kind of oven you're using. So it makes it pretty a high demand device or appliance that takes a lot of power at one time and takes the power away from maybe some other important loads you want to back up, and then also consumes your battery very fast in a backup scenario. Air conditioners are very similar too. Those are on 30 minutes out of the hour, 40 minutes out of the hour to keep the house cool. And it's got a compressor and and fan inside of it. And whenever it's running for 30 minutes, maybe 40 minutes, maybe 20 minutes, depends on how hot it is and what your temperature's set to, it could be quite a bit of power consumed by that too. So I have a hard time recommending folks to back up air conditioners and ovens because of that, because it really is taxing and makes it to where you're reaching the limits of the backup potential for a battery system for how much it can output, as well as consuming quite a bit of power. I showed a few main components there too. The utility grids here to represent in the diagrams. I'm going to show you how it functions with the utility, a normal system. The main service panel, which has the meter usually installed on it, and then a backup electric panel we typically would install for most systems. Not all systems get a backup electric panel. Like the SunVault has its own backup panel inside of its controller or smart switch. And then we have some regular house loads, televisions, microwaves, ceiling fans, lighting, receptacles around the house, to run your vacuum and plug in regular devices, lamps, etc. Those would be considered like the backup circuits. Okay, so as I go through some of these diagrams to explain how it works, I'll show you a little bit about each component and how they function. I'm going to switch back over a little bit to the Enphase layout. And so we've got the controller, the computer, which is the IQ Envoy, right? We've got the smart switch and the batteries. And now while other systems it can be all-in-one type of system, everything is modular for the Enphase system to where you can just kind of replace or add to, etc., things like that for batteries. Let's go ahead and go to the next one. So I'm going to walk you through very different scenarios that will paint the picture, I think, of how the backup system's intended to work. Now, I know that every system is a little bit different, right? But they all almost function the same. And it's rare that they wouldn't function the same way. The only exception I would say is compatibility. Let's say perhaps you have a battery system that can't do what I'm about to show you. That'd be an incompatibility issue where the batteries aren't capable of having the solar function on their own without grid presence. That happens with like the Tesla Powerwall 2 and some older string inverters and older microinverters that may be installed for an older system where you're trying to upgrade and put a new battery on an older system. Not everything's compatible with the Tesla battery systems. Not everything's compatible with the Enphase systems or the SunVault power systems, etc. And so there's some caveats that are there, right? But for what I'm showing you is a walkthrough for compatible systems. Burtech doesn't install systems and highly discourages anybody from using anything that doesn't enable the solar to work when the grid's down. So make sure you are properly educated by one of our, whoever it is you're going with solar. Our representatives make sure that they're pairing a system that's compatible with what you have, if not replacing certain components to make sure everything functions the way it's really designed and intended to. You don't want to have incompatibility issues. Okay, so this is a scenario for the morning time when the sun is kind of still low. It's bracing up in the morning, and there's very low consumption typically in the morning. Usually nobody even has any lights on, maybe a couple lights, and nobody's really doing a lot in the home. Maybe getting ready just to get going, and there's just a couple loads going on. It's kind of a typical morning, earlier morning type time, or once everybody gets out of the house in the morning, headed to work and school. It's not a lot going on, but the sun's still coming up, and so it's producing only a little bit of power. The diagram shows that we're getting about 1 to 3 kilowatts of solar in the morning, depending on the system size and the conditions and weather, etc. And these are just kind of generic diagrams to give you an idea of how it works. So let's say we're getting 1 to 3 kilowatts of solar. It goes and fed straight into the controller or the smart switch gateway, and then that is charging the batteries. So whatever power it can send to the batteries, it's going to send it there. Additionally, it can send power to some of the the backup loads, and so the backup loads would get priority in most cases. And so the power would be going from the solar to offset the power that's being used by your appliances inside the house that are on the backup panel, and anything extra would be going into the batteries. This is the case for most types of systems, and the grid would not really be a part of this. And so as long as the critical or the backup loads are under the amount of solar coming in, and which is usually the case in the morning time, then the grid's stagnant. A lot of times you won't see the heavier loads that are not backed up even doing anything. And so most of the stuff in the house would be running basically off the solar in the morning. And you'll start trickle charging and charging a little bit into the batteries in the morning. Now on the next page, let's say it's getting warm. It's the afternoon time. It could be the winter time too. You're maybe using a heater, maybe you're using the air conditioner. Depends on the situation. And it's not too warm, it's not too cold, or whatever the situation. And so maybe it's not at a low capacity, low usage on it, so it's not being running too much. So I showed the air conditioner consuming anywhere between 0 to 3.6 kilowatts of power. Kilowatts is how we measure power, right? On how much power is being used at a time. And so if you have a situation where the solar is present, right, it's going to continue to charge the battery. And I indicated the battery is a little bit more charged on this slide than the last one. I kind of made it to where we can indicate this, how much battery charge is inside the battery at the time. So in the afternoon, it's about midway now, or midday, 12 o'clock. It's about half powered. It's been charging all morning, and it's still able to take care of the power if they've increased and stuff like that during the day into the backup loads. It's able to take care of those. And anything that's needed for the higher loads, since they're not backed up and the power is not adequate coming from the battery system, would likely come from the grid. And that's just the way the system is designed and typically in how it's laid out. If there's excess power by any chance and the batteries are full, then the power for the solar would then go and help to offset those loads, which I'll show you in the next slide an example of that. So this is kind of typically for about noon for a normal day. However, it could be a little bit different, and it could look a little bit more like this even at midday at noon, even though I noted this for the late afternoon. So late afternoon, we're going to assume that the batteries are full. It's got enough charge throughout the morning and the afternoon. Now we're late afternoon, batteries are completely full. They're sitting there waiting. They have nothing to do because the solar is still producing quite a bit of power. Now we're about 3 to 6 kilowatts of power from the solar. There's only 1 to 2 kilowatts of consumption on the backup loads, and the rest of the power is going to be fed back to the grid. And so you can see the line indicating coming from the gateway there, or the smart switch. The power would then be transferred from the smart switch going to the main service panel. And it would offset any power that goes to the air conditioner, and what doesn't go to the air conditioner or any loads that aren't backed up would then go to the grid. And that would get you your credits, solar credits for the utility based upon what your net metering terms are with them. And so this is kind of the ideal situation. It's not always the same. This could be earlier in the day, this could be later in the day, and sometimes, it depends on the weather. You may not be producing enough power to even do either of those. So it just all depends, and this is kind of just the normal functionality to give you a snapshot of it. All right, now let's go into the evening. All right, so here comes the evening time. The sun's still kind of setting, right? It's almost nighttime. The solar's dropped down to what it was in the morning, 1 to 3 kilowatts of power coming out of the solar, could be less. And then you have quite a bit more consumption on the backup loads. Now I'm showing 1 to 3 kilowatts of consumption because people are coming home from work, people are home from school, they're working, they're doing things. Perhaps you're starting to do some cooking for the evening for dinner. And I know this snapshot is not every person or individual family, but just kind of a ballpark idea of this kind of a scenario and how it works. So we're consuming more power there. We got the oven running, right? I show some power going to the oven, show some power going to the air conditioner, and I actually show power going back and forth to the grid. Now the reason being is I'm showing this is because if there's more power coming from the solar still and those devices are off or cycling on and off, power will go back and forth between the grid here to take care of the loads. Now in the evening also, normally you have a system set up to take care of your time of use savings. And time of use savings is how the utility charges us extra amounts during the evening time. So our cost of power is higher in the evening than it is during the rest of the day and nighttime, morning, etc. in the afternoon, depending on your rate structure with the utility. And so we're able to get some credits there. And we also program the batteries for that case to start discharging. So you see on the batteries now, the batteries are full and they're starting to discharge. And I have it showing it discharging anywhere from 0 to 7.7 kilowatts of discharge. That's because I'm showing 2 batteries there, and each of them put about 3.8 kilowatts of power out. So 7.7 is roughly, 2 of those putting out. And that's the continuous output power. Not the maximum peaks, but the continuous, as I was explaining the difference between continuous earlier and maximum outputs. So they're able to discharge that, take care of the loads for the home, and make up whatever the solar is not covering. So potentially you can have solar output as well as the power from the batteries all at the same time to take care of the loads for the normal backed up appliances, as well as offsetting the power that's being used for the air conditioner, the oven, things like that. And so it just depends on how much you're using at one point in time. Power could be coming from the grid, it could be going back to the grid, depending on how that's calculating out based upon the incidental or immediate power usage at the given time, which is always changing. And so, but this is just kind of give you an idea how that works. All right. Now, let me go and see this situation here. Now, this is at nighttime. All right. So we're showing the battery at a lowered battery state, charge state. And so he's continuing to offset some power and feed power to your backup loads. I'm assuming nighttime, you're not running the air conditioner or not cooking anymore. So your grid activity is basically stagnant and there's nothing's happening there. And so all that's really happening is the battery is able to take care of the appliances that it's hooked up to for the backup system. The solar is no longer active because the sun's gone down. It's not producing power anymore. And then the process would repeat the next day as I started from the first slide indicating what happens in the morning. And that's the normal scenario and process for an everyday routine. Now there's a little bit of a different story whenever the grid goes out, which I'd like to show you now. And a lot of people are always asked the questions about, well, what happens and how come my solar's turned off whenever the grid's out? I don't understand what's going on. And or they see the diagram doing something different when the power goes out, and they're like, oh, what is this? Well, how come it's doing this? I'm going to walk you through a few different scenarios. We're going to show you what happens in the morning, afternoon, evening, and night, again, if the grid's out. Okay. All right. So here's the morning, low sun again, same scenario we started with the first diagram on power usage and production. We're going to show our battery is at low power because it's the morning. The solar comes up, starts powering, the sun comes up and starts powering the solar, and solar is starting to take care of the loads for the house. And whatever power is not being used for the loads to the house from the solar is going to start trickle charging or charging up a little bit more as the sun comes up more and more to the batteries as it continues to take care of the house loads that are backed up. And I put a big red X on the grid there, right? Now the main service panel is no longer going to have power because the smart switch, controller, gateway, whatever your system calls it, in our case it's the Enphase controller too, that is active and still has power on it, but it disconnects itself from the utility grid from the main service panel for safety purposes. Therefore, your appliances that are not backed up, like the microwave or like the oven here and the air conditioner, would not have power. They will not function when the power's out if they're not backed up. Now, depending on your system size, you can back up some of those bigger appliances. I don't recommend it because it's not normally a reliable system that way, to put it. I'm not sure any other way to put it. It's not a dependable or sustainable system. Whenever you back up just what the solar can really handle, it's sustainable. And it's sustainable indefinitely. You can go without power forever on your backup appliances as long as the sun comes up and you get enough sun, right? However, running an air conditioner, running an oven, it's not the case at all unless your system is twice the size that you need it to be and the battery capacity as well. So unless you have the funds to do so, and some people do it and they're able to afford it and that's something they want to do, but it is expensive because you're talking about quite a significant amount of solar and quite a significant amount of battery capacity to purchase to be able to have it function to take care of those items sustainably that are on that side of the screen. So this is what you're going to get when the power goes out. You're going to get the backup loads, whatever's backed up, powered by the batteries, powered by the solar. Now, as the sun comes up and gets warmer during the day or brighter during the day and the sun gets midday, there's lots of sun coming and there's a moderate load possibly and you're still off grid. Okay, the battery charge state comes up a little more as it's charging and the solar is producing even more power and the extra power that it's now generating is definitely going to fill up those batteries and it'll fill up very fast. Okay, and then we come in the late afternoon, the batteries are fully charged. Okay, now we get into some interesting things, and this is what really confuses people too, is they see, wait a second, well, my batteries aren't doing anything, or my solar is not producing as much power as it should produce power. Well, that's because the smart components of the computers that are built into the system start regulating and modulating the system. So if your batteries are in a full charge state, then there's no purpose in discharging them when the solar is still active, as long as the solar makes up the capacity that you need for your loads and your consumption for your backups. Okay, so I'm showing a diagram here that shows 1 to 2 kilowatts of consumption in the late afternoon, and the solar will produce only 1 to 2 kilowatts of solar. Now, I know you probably have to go back and see, but if you saw this same slide for the late afternoon on the grid system, I showed 1 to 3 kilowatts of solar versus 1 to 2 kilowatts of solar in the top left-hand corner. The reason being is because I drew that little dashed line in there that says to match. And so the solar is throttled, right? The system starts controlling and managing how much solar is being produced. And it's able to do that whether it's the microinverters or whether it's an all-in-one system like the NeoVolta, and it modulates and controls how much solar is going to be produced. Or it can just turn the solar off and cycle batteries off and on, and then turn the solar back on to recharge the batteries. And then what the system does is it automatically self-regulates, self-modulates everything, and turns and controls how the solar and the battery is working together to make sure that you're getting the power delivered that's needed for your backup loads, and in a safe way possible too, because it doesn't want to have a bunch of power coming from both the inverters at the same, more power that's coming from the solar, sorry. It doesn't want more power coming from the solar than the loads can handle if the battery is full, because it has nowhere to send the power. So it has to modulate it for safety purposes to make sure that the power has somewhere to go. Okay, hope that makes sense. It can be a bit confusing, but let's look at the next slide anyway and see how it works a little bit in the evening time. Okay, so evening time, the solars come down a little bit, and perhaps you're using a little bit more power in the evening. So you're using 1 to 3. You got 1 to 3 kilowatts of solar coming in from the panels as the sun's setting, so it's less, and going down to working its way down to 0. And you still have 1 to 3 kilowatts that just kind of jumps around depending on what you're using and what you're running. In that scenario, the battery is going to match and discharge whatever the solar's not making up. So if the solar can't meet the capacity for what's being used on the backup loads, then the batteries are going to make up the difference. And they'll make up that difference all the way down until the solar is completely gone. Right? So you'll be able to pull power from both the batteries and the solar while all the grid is out and everything else is not functional. All that stuff will maintain and manage itself, ramp up how much power comes out of the batteries, ramp it down based upon how much power you're using and based upon how much solar is present as well. So it automatically, instantaneously collects all the data for your power usage and makes it ready and available for you to use. Here's the night diagram. Now the sun is down. Now it's just the battery regulating the power for having the available power for you to pull power from the batteries at any time to take care of your loads that are on the backup system. Okay, so now that's hopefully that's clear. Maybe need to play the video again to kind of capture it. But here's a couple of notes to consider. All right. If the battery state is too low, right, because most of the cases what I explained is accurate, but there's a few scenarios. If the battery state is too low, right, then no power is going to discharge from the batteries. It goes into protection mode. There's a set limit, right, typically for the battery state to make sure the batteries are able to recharge and things like that. Even your normal modern cell phones, right, don't actually discharge all the way to 0%. They may show you 0% on there, and some manufacturers for the battery systems you use will show 0% battery. That's not really true. There's actually some reserve in there, because if you discharge a battery all the way down, you can't charge it again. So there is a shut-off and cutoff point. Like NeoVolta has a 20% cutoff point. I think Enphase, Tesla, they show 0, but it's really still 10 to 20% in there. Of battery state and charge. They just kind of cap it and stop, and they don't discharge power anymore to make sure the battery is able to recharge itself again, and that they can ensure your warranty, right, for the life of the battery. And so that's just not going to happen. Okay, it disconnects. Okay, in-phase disconnect issues can occur as they communicate locally, wirelessly, etc. If disconnected from an IQ Envoy, the batteries will not discharge. That's the same case with the Tesla, the NeoVolta, or Franklin, any battery system out there, if there's any lapse in communication where a wire or a wireless communication is not there, not happening, and the controller or the brains, the computer for the system cannot talk to the batteries, then it goes in a safe mode and a standby, and they just won't discharge. So if you have any issues with that, you see any errors or something like that for connectivity for them, they're not working, unfortunately. It's just if it's not talking to the computer for safety purposes, it has to just go into standby. And so there is some caveats. I know Enphase has some difficulties with their Zigbee or Bluetooth communication they use between devices. Sometimes you'll see that on monitoring where it disconnects, and unfortunately, until that communication is reestablished, the batteries aren't charging or discharging. And it doesn't happen that often. I have seen it a little bit more with Enphase than I have with other systems. I know Nevolt, I rarely see any of that, but it does happen. I know LG had some major issues with their batteries too, with the Solar Edge system when they were launching those a few years ago. But it's just a normal problem, and due to safety concerns, it's built in the programming to not work, and if there's lapse communication. So if you see that, don't be too alarmed. If it doesn't clear on its own within an hour, a couple hours, sometimes they have artifact type alerts on there, even though the system's working, where the warning still sits there for someone to look at the manufacturer company to see that there's an issue. But it's not really a concern. It does happen, but it usually fixes itself. Poor weather. Batteries are supposed to enable backup mode only to reserve power. So sometimes you won't see your battery discharging, and it might raise an alarm for you. Like, oh wait, how come my evening time battery power is not taking care of my loads in the house and it's not discharging? Well, check the weather, because a lot of the systems we use now have built-in weather tracking, and if there's impeding weather that are concerns, then the system's already programmed to go into backup mode only instead of being the time of use offsetting mode. And they do that because in case the power does go out, it makes sure that you have the optimum amount of battery storage capable for you to last the duration of the power outage versus discharging in the evening. So that is something that's present, built into a lot of the firmware, something to look out for. It's not all the systems have it, but I would say most of them do. And there might be other factors and things like that to be considered with different kind of scenarios that may or may not occur with functionality. But in general, this is a really good snapshot of, I think, of how the batteries function and work, and why you might see different scenarios where the solar's not working or battery's not discharging. And that kind of should show you, hopefully, a good idea of how it works. Thank you. If you have any questions, always feel free to reach out to us at BirdTech. We're here for you guys. Our motto, like we always tell people, is to get educated and not sold. We're an electrical contractor. We do several different contracting aspects out there. But batteries is one of our favorite scopes of work. They're really cool equipment and they're fun to see what we can do with them. It's really cool tech, and hope you enjoy it as much as we do, and we do the best we can to serve you. So have a great day.